So it's a three-span continuous beam ABCD, and it is fixed at A and continuous over supports B, C, comma D. And also the degrees of freedom, that is degrees of freedom for this continuous beam is going to be 3. Displacement technique, first we have to analyze what is the degrees of freedom for this problem, so that we can able to find the unknowns, and based on the unknowns the joint displacements can be found, and if you're adding with the fixed end moment you can get the final moments. And also the special thing about this problem is one external moment is acting at the mid of the mid of the span BC. Usually normally loads will be acting on the spans, but this beam is subjected to moment at the midpoint of the beam, span BC. So first span AB, it is having central concentrated load, and then it is followed by the external moment, and it is followed by the UDL, which is 10 kilonewton by meter acting throughout the span CD. So since end A is fixed, theta A is going to be 0, theta B and theta C, theta D are unknowns. So first of all we have to find the fixed end moment. Span AB having central point load, so WL by 8 is the expression. Left side minus WL by 8, right side we are assuming span FEBA is plus WL by 8. So you substitute WL by 8 minus 30 kilonewton meter plus 30 kilonewton meter on the other side. FBC, the moment 50 kilonewton by meter, external moment is acting. So FBC is m by 4, 50 by span length 4 plus 12.5. And then FBC, then FCB, next span FCB, that's also plus 12.5. Then the next span is FCD, it is with UDL, so minus WL square by 12. You can get minus 13.33 kilonewton meter. FDC is plus WL square by 12 plus 13.33 kilonewton meter. Second step, we have to frame the slope deflection equations for the 6 values. Actually we have 3 spans, so 6 equations will be generated. So FMAB, it is fixed moment is minus 30 followed by moment due to the joint displacement 2A by L, 2 theta A plus theta B. So theta A is 0, so remaining terms theta B will be there. You substitute L for that span length for the span AB. So minus 30 plus 0.5 EI theta B. Similarly MBA plus 30 plus EI theta B. MBC plus 12.5 EI theta B, 0.5 EI theta C. Theta B, theta C will be there, it is unknown. Similarly on the other end, MCB equal to FCB 2 EI by L, 2 theta C plus theta B. So you substitute the L values and simplify, you can get equation 3 and 4. For the next span, you substitute L value and frame the equation, and you simplify, we can get equation 5 and 6. Equation 5, fixed moment is minus 13.33, 2A by L, L length is 4 meter, 2 theta C, theta D. So you substitute and simplify. MDC is FDC plus 2A by L, 2 theta D plus theta C. So I simplify this and you can get the equation 5 and 6. So if you want to solve 3 unknowns, we need 3 boundary conditions or joint displacement conditions, and we can take 2 joint displacement joint conditions and 1 hinged end conditions. Since D is hinged support, we can take the final moment MDC 0. And summation, first condition is generated by taking the joint displacement condition, joint moment condition. Summation of the moments meeting at the joint is 0. Say MDA plus MDC 0, MCB plus MCB 0. Simplify this, you can get the equation, and equation 7 and 8 will be there, and MDC equal to 0. So you add MDC and that's going to be 0. So next, by solving equation 7, 8, 9, we will get EA theta B minus 24, EA theta C plus 11, EA theta D minus 18.9. Substitute the values theta B, C, D in respective equations. You can get the final equation. MAB minus 42.02 kilonewton meter. MBA plus 5.96 kilonewton meter, MBC minus 5.96, so that you can check the summation of moments meeting at the joint is 0. That condition is satisfied. Plus 5.96 minus 5.96. MCB and MCD, that also satisfy the condition. MDC already we know it is 0, so that is also satisfied. So if you know this final moment, immediately you convert all the span into simply supported spans, and the moment what we found is marked in red marks. So anti-clockwise negative and clockwise is taken as positive. So you put all the values and find the reactions simply by using the static equilibrium conditions. Structure becomes statically determinate, so static equations alone can be taken and it is found. So RB20, RE38, 30 and span BC. This is RB2, so this is 13 and this is RC 13.2. So this final span also RD, RC values. So with these values we can plot the BMD and SFD. First BMD is plotted. For finding the BMD we should know the span moments also. First span, central concentrated load is acting, so WL by 4. Second span, external moment itself is acting. And third, it is subjected to UDL, so WL square by 8. Substitute all the values. We can substitute WL square by L 8, W is 10, L square is span length by 8. You can get the moment 14.62. So if you know the span moments and joint end moments, you can draw the BMD. And next, similarly, we can plot the shear force diagram. 38 and here 20, 13.8 to 22.9 and finally 17.09. So I can plot the bending moment diagram, shear force diagram, and with